Good morning, my chemistry students, and welcome to your last actual class that we will have for the whole year. I've enjoyed being with you guys. I wish I could see your faces and tell you bye, but maybe at graduation. I'm going to go ahead and get into the review because I'd like to go ahead and finish that today. I know I said in the text message that I was going to release the exam after class, but I went ahead and put it on Homeschool Minder. So it is there for you in a PDF form, just like the other practice exam was. So it's attached there. And if you have any questions, just reach out, and I will be here on Zoom at 9 tomorrow to answer any other questions that you might have about your exam. So I'm going to go ahead and jump back into the review where we were. We were on practice question number 17, and I'm going to go ahead and go to that for you. I think I've got more of a hang of it today. Okay, so number 17 says, give the balanced chemical equation for the reaction that occurs between nitric acid and magnesium hydroxide. I went ahead and typed it out. So nitric acid, this is going to be an acid-base reaction, which you should know because we have a nitric acid and then we have magnesium hydroxide. Hydroxide is a base. Hey, Garrett. I'm starting on number 17 in the review. And okay. All right. So what we're going to do is put our acid first. We're going to add that to our base. You do need to know magnesium and hydroxide's formula there. So magnesium is just Mg. Hydroxide we know is OH. So we would look at our periodic table to find the charge for magnesium. It's in column 2, which means it has a +2 charge. And I know that hydroxide has a -1 charge. So because they're different charges, I'm going to switch them, which means the magnesium is going to get a 1 subscript and my hydroxide's getting the 2 subscript. So that's why we have that right there. And then we know in this kind of reaction, it's going to produce water and a salt. So here I have water, H2O, and we know that since there's 2 hydroxides, there has to be 2 hydrogens to receive that. So I'm going to have 2 H2Os. And then we're going to combine what's left over here, which is the magnesium and the NO3 on this side. So magnesium with NO3, and NO3 is also a ion, sorry, a polyatomic ion. So we're going to go to page 175 to find the charge. That is nitrate, and its charge is -1. So again, we have a charge of 1 and a charge of 2, so we're going to switch them. So magnesium gets the 1 subscript, and the nitrate gets the 2 subscript. Second step here, I just balanced. So like I said, we need the 2 H2Os to accept the 2 hydroxides, and we need 2 hydrogens as well. So this is your balanced equation for number 17, the second one. All right. Number 18, unless you have any questions, we good with that one?
Nope, I'm good.
Okay. Number 18, a mixture of 1.3 grams of N2 and 1.6 grams of O2 has a pressure of 1 atmosphere. The partial pressure of each gas in the mixture is blank. Okay, so what we're going to do first is we're going to use our mole fraction, but they give us grams. So the first step here would be to convert to moles. So let me go here and do the whiteboard, and we'll convert. So we have, looks like, how many grams? 1.3 of N2 and 1.6 of O2. 1.3, I'm actually just going to type it, it's easier. 1.3 of N2, and then we had 1.6 of O2. 1.6 O2. All right, so like before, this is going to go over 1, and this was grams. Sorry, I forgot to put the G in there. All right, and then we need a conversion factor. So I'm going to moles. 1 mole is going to be on top, and I need to find out how many grams are in a mole of N2. So I'm going to look at the periodic table. Nitrogen has 14 grams. So because there's 2 of them, I have 28 grams. You would put that in your calculator. So 1.3 divided by 28. Just going to do that real quick. you're going to get 0.0464. 0.0464, and that's moles of N2. Okay, next we're going to work on oxygen. So this is going over 1. I need a conversion factor. 1 mole is going to go on top like normal because I'm going to moles, and I need to know how many grams are in 1 mole of oxygen. So I have 16, and there's 2 oxygens, so that's going to be 32 grams. Put it in your calculator, 1.6 divided by 32. You're going to get 0.05 moles of O2. Oops. So now I have moles for each. So then the next step is going to be to calculate the total number of moles in the mixture. So let me go back to my whiteboard. Where did it go? Whiteboard. Okay, I don't know where the whiteboard went. All right, but you're just going to add them up. So what did we have? We had, oh no, this is the real exam. What is happening here? Sorry, my screens are all crazy. Okay, here's the whiteboard. All right, so we have 0.05 plus 0.0464. So you're going to add them together. Your total number of moles is going to be, it's going to be 0.0964 moles, and that's total. Okay, so then your next step is going to be to plug it in that mole fraction equation and figure out what fraction of each they're taking up. So you have first N2, and you're going to use the number we found here, so 0.0464, and you're going to divide by the total number of moles, 0.0964. And you get 0.48. All right, then we're going to do the same thing for O2. You're going to do 0.05 divided by the total number, 0.0964. And let's see, you get 0.51. Really, it's 0.52 if you round, which makes sense because if you add them up, this is going to equal 100. And then you would multiply by the total pressure to get the partial pressure of each gas, but the pressure is just 1 atmosphere, so you're just doing times 1. So what you're going to get for your final answer is 0.48 atmospheres for N2 and 0.52 atmospheres for O2. All right, number 19. What is the volume of 16 grams of carbon dioxide at standard temperature and pressure? I think you got this one wrong, Garrett, so this will be a good review for you. We are going to use this equation. Let me see if I can find the whiteboard. Why? I'm struggling. Okay, to keep my screen straight. All right, so we're going to use this equation. PV equals nRT. Okay. Now what we're going to do is rearrange it to solve for volume because they're asking me what is the volume. So we're going to rearrange it. We just divide both sides by P, right, to get the V by itself. So V equals nRT divided by P. Okay, now what we have to do, they give us temperature, they give us pressure, they give us grams. So what we need moles, because that in there, remember, represents number of moles. So first I'm going to convert 16 grams of carbon dioxide to moles. So 16 grams of carbon dioxide over 1, oops, sorry, times a conversion factor. And I'm going to moles, so 1 mole on top, and I'm going to find out how many grams are in 1 mole of carbon dioxide by looking at my table. I have 12 for carbon, and I have 16 times 2 for oxygen, so 32 plus 12.
44.
So 44 grams in 1 mole. So in your calculator, it's going to end up being 16 divided by 44. And that's going to give you 0.36 moles. All right, so now I have N, and I have temperature, and I have pressure, and R was the constant that we talked about. Let's see. Okay, so we're just going to plug everything in. So I have V equals, and N was 0.36 moles times that R constant, which is 0.0821 liters times atmospheres divided by moles times Kelvin, weird unit, times temperature. Standard temperature is 273 Kelvin. We have to use Kelvin there. All of that, so I can put all of this really in parentheses to help me out. Let's see. All of that divided by pressure. Standard pressure is 1 atmosphere. Okay, so really this doesn't even matter because anything divided by 1 is the same. So in your calculator, 0.36 times 0.0821 times 273. And that's going to give you 8.07 liters. Ooh, I got the wrong number there. My bad. Change it for you. Wonder why I got a different number that time. I'm not sure. All right. So the answer would be C. Number 20, does an apple have potential, kinetic energy, or both? And we know an apple has potential energy. It is not energy in motion, but it is stored energy. 21, the following reaction is performed in a lab. If 190 milliliters of 1.25 molarity aluminum nitrate is added to an excess of sodium sulfate, how many grams of aluminum sulfate will be produced? And I know we kind of talked about this one before, but for everybody else, I'm going to just go over it quickly. So first of all, we know this is a stoichiometry question because they give me an amount of one substance and they're asking for an amount of another substance in the equation. So we know with stoichiometry, we always are going to need moles, first. So we have to get this amount that they gave me in milliliters, we have to get that to moles. So first of all, I know this concentration molarity means moles per liter. So I have moles per liter here and I have milliliters. So I'm going to convert this milliliters to liters so that I can use it to get my number of moles. So I'm going to go 190 milliliters to liters. Now for me, you could do your conversion factor and do 1 liter over 1,000 liters. So really you're just dividing this by 1,000, which tells me I'm going to move the decimal back 3 places. So that's going to equal 0.19 liters. Okay, so then I'm going to do that number, 0.19 liters, and I'm going to have to do a conversion factor here. I'm converting to moles over 1 times, and I'm going to do what they gave me, which was 1.25 moles per liter. 1 liter. And that will give me how many moles I have. So in your calculator, 0.19 times 1.25. And I got 0.2375. 0.2375. All right, so now we have the number of moles. Okay, so now we have the number of moles of aluminum nitrate. And now they're asking me, let me go back to my question, for moles of, well, for grams of aluminum sulfate. So now I'm going to go from moles to moles. So I have the value of this one here. I'm looking for the value of aluminum sulfate, which I know is this substance here. So I'm looking at the coefficients. So for nitrate, I have a 2, and for sulfate, I have a 1. So now I'm going to have to do a conversion factor. So this is my starting value, what I just found there. Moles of aluminum nitrate. That's going over 1. I'm going to do a conversion factor for this. And it's going to be the number of moles of sulfate on the top, because that's what I'm going to. And I think that was SO4. Oh, I don't remember the other number. I'll plug it in a minute. And then I know I had 2 moles of aluminum nitrate. That's going on the bottom. Let's see. SO4 3. Okay. Close enough. All right. So then in your calculator, you are going to do 0.2375 divided by 2. And that's going to give you 0.11, I'm going to say 9, I'm just going to round, and that's moles of aluminum sulfate. Now I'm going to go from moles of aluminum sulfate to grams of aluminum sulfate. So 0.119 moles is my starting value. And I'm going to put it over 1. Conversion factor, I'm going to grams. This should be like second nature by now to everybody. We're going to have 1 mole on the bottom. We're finding out how many grams are in 1 mole of aluminum sulfate. If you were to look at the periodic table, you're going to do the mass of aluminum plus you're going to do the mass of sulfur times 3, the mass of oxygen times 12, because we have 4 times 3 here, and add all that up. And if you do all that in your calculator, which I'm not going to waste time doing, you'll get 342.3 grams. And then you're going to plug all that in your calculator. So 0.119 times 342.3, you should get 40.73. And let's see how many significant figures we need. They're giving me 2 significant figures here actually, and 3 here. So we can round it to, let's see, 41. So 41 grams of aluminum sulfate is your answer. Okay. Number 22. A chemist needs to know the concentration of some KOH that is in the laboratory. To find this out, the chemist titrates a 50 milliliter sample of the solution with the 2.5 molarity HCl. If it takes 14.7 milliliters of the HCl to reach the titration endpoint, what is the concentration of the KOH solution? So this is a lot of numbers and words, but we need to figure out what they're asking. So first, we need to know that titration is always going to be a stoichiometry question. So if you see that word titration, you're going to be doing stoichiometry. So that tells me I need moles. So in order to use stoichiometry, I also know I'm going to need a chemical equation. So let's do that first. So our chemical equation, we're using HCl. Autocorrect. Stop. Okay, HCl plus, we are going to use KOH, and that's going to make, we're going to switch these. So this is acid base. So my hydrogen is going to combine with my OH for H2O. And then my potassium is going to combine with my chlorine. And I'm going to need to look at the charge for potassium and chlorine. Potassium is a 1, chlorine is a -1, so we're good there. Okay, so this is already balanced, so I have my equation. Now what I need to do is calculate how many moles of my acid I have, because they're asking for the concentration of the base. So first we're going to start with the acid since they gave me that amount, and I need to know moles. So they gave me milliliters. They also gave me concentration. So I know I can go, if this is molarity, moles per liter, I can figure out how many moles from there. So what I'm going to do is use the 14.7 milliliters, and I'm going to convert that to liters. So let's clear this out. So if I have 14.7 milliliters, I know I'm going to move the decimal back 3 places. That's going to be 0.0147 liters. That value is going to be multiplied by my concentration, just like we did in the last question. So we have 2.5 molarity. So 2.5 moles, and that's per liter. So my liters are going to cancel and I'll be left with moles. So 0.0147 times 2.5. And you're going to get 0.03675. And that's moles. All right. Now we're going to go from moles to moles. So we're going to go from the moles of our acid. This was HCl. And we're going to go to moles of our base. So this is my starting value now. And that's moles of HCl. And I'm going to moles of my base. So I'm going to have to look at the coefficients in my chemical equation. And they're both 1. So really, if you would like to skip this step, you can. Because you have 1 mole of KOH and you have 1 mole of HCl. So you're going to end up with the same number, 0.03675, and that's moles of KOH. All right, so now we need to divide by the volume to get concentration, because concentration, like we just talked about, is moles per liter. So if we divide our number of moles by our volume, which is liters, then that will give us concentration, moles per liter. That'll give us molarity. So the amount that they give me is, let's see, 50 milliliters. So first I need to convert that to liters, so I have the right unit. So I have 50 milliliters. And that's going to equal, I'm moving the decimal back 3 places, 1, 2, 3, I'm going to add a 0, so 0.05 liters. So I'm going to take my moles that they gave me, or that I figured out, moles divided by 0.05 liters in your calculator. And that's going to give me 0.735 molarity, because I have moles per liter. And let's see how many significant figures we need. We need 2 because this is the smallest they give us. So I'm going to just round and say 0.74 molarity. I will say this is the exact same question on your final.
That's good to know.
Yes.
because I forgot how to do that one.
That one was very difficult because they give you volumes and concentrations, and it's a lot of things going on. But once you think it through, it's kind of simple. All right, so you should be set on that one. Let's look at 23. A 30-gram piece of copper, and they give you its specific heat capacity, which is that C value, at room temperature loses 856.7 joules of heat. What is its new temperature? All right, let me go back. Okay, so first we are using this equation here. I'll write it out for you. Q equals M times C times change in temperature. This is our main equation that we're going to use. And we have to rearrange it because they're asking for a new temperature. So I'm going to rearrange for temperature. So I'm going to divide this side by M and C and this side by M and C. So then I'm going to have change in temperature equals Q divided by M times C. That's my new equation. Then I'm going to go ahead and just plug in the values because I have everything it's asking for. I have the Q is the energy that they told me was lost. And then I have C, the specific heat right there. And then I also have grams, I have the mass. So I have everything I need here. So let's just plug it in. Change in temperature equals 856.7 joules. And remember, that has to be negative. I almost forgot because it lost heat. And then mass times C. So the mass is 30 grams. Times that C value they give me is 0.385. I'm not going to write out the unit because it's all going to cancel out. And that's going to give me in the calculator, let's do negative 856.7 divided by parentheses 30 times 0.385. And I get negative 74.17. That was my change in temperature. Now let's go back and see what it's asking. It's asking for the new temperature. It started at 25 degrees Celsius. So what we're gonna do is subtract 25 degrees Celsius minus that change in temperature there. It's negative, which means it's a minus, not a plus. So 25 minus 74.17. And that would give me, let's see, 25 minus 74.17. If this was a positive number, you would just add. And that's going to give me negative 49.17 degrees Celsius. And I need, 1, 2, 3, I need 2 significant figures. So we're just going to say negative 49 degrees Celsius. That was its final temperature. Does that make sense?
Yes.
Okay. And number 24, I know we discussed, but I'm going to also go over it for everybody. I'm going to go ahead and tell you before it cuts me off, I'm just going to take 27 out, and I'll give you credit for that one. I'll change it today because that was a very difficult question. I went back over it yesterday, and I'm like, this probably wasn't a good one to put on here. So I'm going to take that out, and I'm also not going to include that one on your final. So just take 27 off of your review. So we have 3 left. Hopefully it doesn't run out of time. All right, a calorimeter is filled with 180 grams of water at 22.1 degrees Celsius. A 50-gram sample of metal at 100 degrees Celsius is dropped in the calorimeter and causes the temperature to increase a total of 3.4 degrees Celsius. What is the specific heat of the metal? Ignore the heat absorbed by the calorimeter. Okay, so actually we're going to use the same equation here. So I'm going to leave that. And first, we need to find our Q's. Since this one is using a calorimeter, remember we're going to have to find the Q of the water, the Q of the calorimeter. So first, I'm going to do Q of the water And that's going to be the mass they gave me. So let's see, they gave me 180 grams times the C value for water is always 4.184. And then the change in temperature, so let me see. It went to, okay, the change in temperature they said was 3.4. 3.4. Remember, it's change in temperature, not actual temperature. So 3.4 degrees Celsius. Make sure I did that right. So we'll put that in the calculator, 180 times 4.184 times, oops, I did plus, times 3.4. And I'm gonna get 2,560.6, and that's joules. That's how much energy the water gained. Now it says to ignore the Q of the calorimeter, so that one is just gonna equal 0. I'm not even worried about that one. So then remember our formula to find the negative Q of the metal is going to equal the Q of water plus the Q of the calorimeter. Well, the Q of water, the Q of the calorimeter is 0. So it's just going to be the number for the water. And in order to fix it, I just switch the negative sign over to the other side. So negative 2560.6 joules, which makes sense. If the water absorbed that much heat, that means my metal released this much heat. And let's go back and see what they were actually asking. They said, what is the specific heat of the metal? Okay, so now I need to rearrange my equation up here to solve for C. So I'm going to divide this by mass and change in temperature to get C by itself. And then I'm just going to plug in my values. So C equals the Q of my metal, negative 2560.6 joules, divided by the mass of my metal is 50 grams. Times the change in temperature. So we have to remember we're going from 100 degrees Celsius, and then it had a increase of 3.4. Hold on, let's see. Oh, what am I doing wrong? Okay, so what am I doing here? I got lost for a second. Why do I have a different number? Let's see. Okay, 22.1, but it looks like this had a different number. Hold on, sorry. Okay, so we're doing final temperature minus initial temperature. So I need to figure out my final temperature of the water. So the water was 22.1 degrees. I'm gonna add that 3.4. And that's gonna give me 25.5 was the final number. So let me kind of get over here for a minute. So we had our starting temperature of our water plus the 3.4 temperature change is gonna give me a final temperature of 25.5. And then we're going to do that minus the initial temperature of the metal, which was 100. And that'll give me my temperature change for the metal. So 25.5 minus 100 is negative 74.5. So now I'm going to plug that in over here. Negative 74.5. Okay, so in your calculator, negative 2560.6 divided by parentheses 50 times negative 74.5. Be careful with all those negative signs. And I got 0.6, let's see, 0.6874. And the C would be, let's see, joules over grams times degrees Celsius. And significant figures, we need, looks like 3. So I'm going to round this to 0.687. I will also say that your questions on the final are exactly like this with numbers changed. So this one will look exactly the same, just one number value might be different.
Okay.
Okay, any questions on that one?
No.
Okay. All right, number 25, use Hess's law to determine the change in enthalpy for the combustion of liquid methanol. Okay, let me go over there to that one. All right, so first of all, you get half of your credit just for a balanced chemical equation here. So first you're gonna need the chemical equation in order to solve for your change in enthalpy. So your chemical equation, let's see, we're doing combustion. So our substance that they give us, which is CH3OH, and we have to put our phases here. So liquid, because they tell me it's liquid methanol, plus, and then remember we need oxygen gas for combustion. And that's gonna produce CO2 and H2O, as you remember from lots of modules ago. Okay, now we just need to balance it. So I'm not gonna go into how because you already know how to do that. I'm just gonna plug it in and then later you can go back. Okay, so that's your balanced chemical equation. That's half your credit already right there. And now we just need to look at table 13.2 in your book.
Are you sharing your screen?
What?
Did you put it on the screen?
Did I put what on the screen?
That balanced chemical equation.
Yeah, can you not see it?
No, I see the last problem.
Number 20, do you see number 25 at all?
No, I see number 24, like the whole problem.
Okay, I'm gonna go back. Can you see it now?
Yeah.
Okay,
Yeah,
sorry about that.
That's fine.
All right, there's the chemical equation. Now we're just looking at table 13.2. And what you need to remember specifically here is that you're doing products minus reactants. So let's look at the values. So we'll start with CO2 and H2O, right? So I'm just gonna put change in H equals. And then we'll start with CO2 in the table. Let's see, where are we? And that's in gas form, negative 394. I have 2 moles of it. So 2 moles times negative 394. And you know that's kilojoules per mole. Minus, or plus, sorry, plus. And then I've got H2O, and I forgot to put our phases here. This is gas. Whoop. And H2O is also a gas in combustion. Okay, so I'm looking for the value for H2O gas form, negative 242, and there's 4 moles of it. Phases are very important here, so don't forget that. Okay, all of this, I'm gonna put it in brackets. All of this minus, we're gonna do our reactants now. So I'm looking on that table for CH3OH in liquid form, negative 239, and I have 2 moles of it, so don't forget that. And remember O2, since that's in its elemental form, that's just gonna be 0. So I'm not even gonna worry about O2 right there. Okay, so in your calculator, big parentheses, 2 times negative 394, close one set, plus another set of parentheses, 4 times negative 242, close your other set, minus, and then a whole nother set of parentheses, 2 times negative 239. Be careful with parentheses and negative signs here. I'm just gonna do it real quick and make sure I get the right answer. And I got negative 1278. And of course, the unit there is kilojoules. And it looks like this is the same exact question that's on your exam. Understand all that? Good?
Yeah.
Okay. All right, number 26, last and final question. What is the change in G for the following reaction at 298 Kelvin? So let's see. This is another just kind of like that one. It's the same with using Hess's law, so we can use that table for the change in G. So let's see. They give us the reaction. So I'm doing the exact same thing I did in the last question. I'm just using G instead of instead of H. So change in G equals, and remember I'm going to add up my products and then subtract all of my reactants added together. Again, we have an O2, so we don't have to worry about that one. So let's go ahead and start first with the product.
I was close on that last one.
What? You were close on?
I was close on it. I had 1286 instead of
I saw that, and I wasn't sure why.
I miscounted the CH3O2 or OH, and I put 2 instead of 3. So it was just like one thing off.
Oh no, I knew you were so close, but I couldn't figure out where you messed up at. Well, you're going to get credit for 27 too, so that should help you out a little bit. That'll bring it up to an 80, I believe.
It's better than a 16.
Yeah, much better than that. All right, let's see. So we've got 12 CO2, so 12 moles times, and then I'm looking for CO2 in the gas form on the table. Again, do not forget to look at the right phase. That's going to be, and make sure you're looking at the right table too for Gibbs free energy. Negative 394. I think this is exactly the same as well as your test, your final test. I tried to keep the module 13 ones the exact same because those were difficult since we just learned it. Okay, so 12 times negative 394 plus, and then I'm going to do H2O in gas form. I've got 6 moles times, and let's find H2O. It's negative 229. You can use the chart in your book, or you can use the chart on your module 13 test. It's on there too.
Okay.
All right, there's the products, and we're going to subtract our reactants. Whoops. So C6H6, and there's 2 moles of it. And that's going to be in liquid form. And that's going to be 125 kilojoules per mole. Okay, and then again, O2 is just 0 because it's an elemental form. So in your calculator, don't forget negative signs in parentheses. And I got negative 6,352, and that would be kilojoules. Oh, you know what I need to do is go back and edit I didn't take 27 off of your final yet on the one that I posted on Homeschool Minder. So I'll go fix that. And that should be it, unless you have questions.
Nope.
All right.
Wait, what was the answer?
Negative 6,352 kilojoules.
Okay.
I will be here tomorrow at 9 o'clock, but if you want to go ahead and start working on your exam so you have questions ready, that would be good.
Okay.
All right. Let me know if you need anything.
All right. Thank you.
You're welcome. Thanks for coming. Bye.